course, probability, most of the cases, the time variable is not there. That means they are actually not dynamic. You toss a coin, the experiment ends there. You roll a die, experiment ends there. Even if you toss a coin 10 times, but the experiment is not actually having a time parameter. However, in real life, what happens? We encounter in many scenarios, examples, applications, where actually the randomness continues over time. It actually time dependent. What happens? The number of packets, if you consider entering a server, a router. So it is not actually static things. Packets are coming one after another into the input ports of a router, and the number of packets that arrived up to a certain time varies. Day to day, month to month, time to time. Number of hits in a web page. If you start at a certain time and you go up to a time t, the number of hits actually will not be same for equal duration of time at different time periods. So these randomness are actually time dependent. They are evolving. They are actually changing over time. The signal strength of a mobile phone, as it actually moving from the cell station or base station, or even due to some ambient conditions, the signal strength is never, or most of the times, not constant. So in all cases, what actually we are observing that we have random values or randomness that are time dependent. Actually, such random phenomena that evolves over time, that is time dependent, is or are modeled by stochastic processes. So our actually shift here is from the course probability to random process or stochastic process, is that along with the randomness, we also actually consider time dependency of the systems, process, whatever you say. Okay. And we will try to model things that are time dependent. What are the topics that we will cover here? We will actually try to make it clear what is the definition of a random. Just a minute. Let me receive the call. This is from IoT. Sorry for the interruption. It was an admission related issue. Still, the admission is not closed this year. Maybe it will be closed next week, inshallah. Anyway, so we will be covering basic definition, and we will try to cover some or few examples of random processes, so that basic properties of the random processes can be actually understood by us, so that the later chapters, whenever we will say random process or stochastic process, we will understand what it is. Then actually the ensemble concept, the word ensemble is used in many different ways. In machine learning, it's a very common term, but in our case, it's a very simple and very close term to sample space. We'll just define it. And the probability models that actually are available for random processes or that are associated with random processes. Then we will consider the stochastic process that are stationary, because throughout the course, the random processes or stochastic processes that we will be considering will be stationary. So we need to know the meaning of the term stationary. And one term that actually we will need for solving some special types of stochastic process is ergodic, whether the process is ergodic or not. We try to define this term here. And whenever actually we will really consider such processes while solving for different parameters, we will actually make it more clear what is ergodic. Now, the basic definition of a stochastic process, we will extend the definition of random variables to define a stochastic process. Now, day before yesterday, I actually asked many of you, what is a random variable? Is anyone here wants to be a volunteer to make it clear what is a random variable?
Sir, a random variable is a variable that contains the result of a random experiment, the outcome of a random experiment.
Okay. For example, you toss a coin and the outcomes are heads and tails. So can a random variable X contain a head or tail?
Yes, sir.
How?
It can be only one of these. So basically, a random variable will contain the outcome of an experiment. So we have to first conduct the experiment, and then X will have the value, which is the outcome.
Okay. Anybody else? We'll actually, your definition requires minor corrections. We will make it clear just very shortly. But anyone else wants to add something here? So our objective is to extend the probability model of random variables. We will extend to define a stochastic process or processes. Now, how do we define a random variable? Random variables, X actually is a function of the outcome of an experiment. So here you call it stored H. It is not. It is a function of the outcome. It is not actually storing outcome. It is a function of the outcome of an experiment. And what it does, it maps its outcome W into a point on the real line. That means you can consider into a real number. So if we have an experiment here, we always will have a sample space, and outcome is here. And this is our real line. So 0 is here. Random variable actually is a function that will map this outcome of W into a real number X here. If we have another outcome, say that will be mapped to another random number, another real number, X2. So X, a function of the outcome, and while actually telling that this is a random variable, usually we do not use the argument of the function. We simply use the term X as the random variable. But inherently it's a function that actually maps the outcome into a real number. So when we have it, x actually maps this one into what? 1. Tail to 0. And here actually is the function. But while representing this one, since we know it is there, we actually make it clearer, make it simpler. We say it is x, who is mapping the outcome is to 1 and outcome t to 0. So I think it is clear now that the random variable is the outcome mapped into a real number. And now for a stochastic process, since we mentioned that we extend the concept of random variable, and to extend it, the shortcomings of the random variable is actually overcome. And what is the shortcome? It cannot actually handle time. That's why we extend the concept of random variable by including the time parameters. Then how we define it? We define it very simply. Like the random variable, it is also a function. Function of what? The outcome of an experiment. So it's function of W once again. Now, what is the difference here? If W is fixed, then the real number is fixed. Whenever we have head, we get 1. Whenever we have tail, we get 0. But here, the interesting thing happens here. That maps is W to different real numbers at different times. So at T1, the mapping from say W to real number may be 1. At T2, it might be 0. How can we get this? That at different times, different values will be mapped. And such mapping actually can be obtained instead of mapping W to a real number, if we map it to a time function. For example, if you map it to a, say the head is mapped to a sine function. Now, if you say what is the real number associated with the random variable or the random process something, if head appears at time say T1, it might be close to 1. At time T2, it might be negative 0.25 or something like this, or 0.5. So as time passes, the value changes. So the connection is very simple. In case of a random variable, we map the outcome of an experiment to a point. So the mapping is always 1 to 1. It could be many to 1, sorry, it could be many to 1 even. In that case, we call it an event. Could be many to 1, but the mapping is static. So whenever you run the experiment, it will return the same value. But in a stochastic process, as it evolves over time, the mapping itself is random. Or you can say the mapping changes time to time. So the mapping actually is different real numbers at different time, and we achieve this by actually mapping the outcome of the experiment W to a time function. So usually in the sample space, if we have n elements, that could be at most n such time functions. Multiple outcomes could map to a single time function. That is also possible, but at most n time functions. So there will be many functions, and the outcome of the experiment will be mapped to a particular time function. So that mapping is one outcome, one time function. Multiple outcomes can be mapped to a single time function, but for one, it is fixed. And since the time function actually is changing its values over time, so at different times, the real number to which actually a particular outcome is mapped will be different. Any questions here? So this idea is very important. Actually, one of the most thing that we are learning here. So formally, we can define a stochastic process as a function, or it's a function of what? Element of S. And according to our assumption that it returns different values at different times, it maps different values at different times. So as well as it is a function of another independent variable, t. This t, most of the cases are related to time, but there are situations where it might not be time. There are such cases. So given an experiment with sample space S, we now denote a stochastic process like this. See the difference between a stochastic process and a random variable. A random variable actually is a function of the outcome omega. So it's a function x of omega, and a stochastic process is function of two elements. They are independent, omega and t. And maps is possible outcome omega to a time function xt. And this, as we know, how a particular outcome is mapped to a real number, it depends on some rules. Rules are governed by the experiment. Here, the random process form, how these actually outcomes are mapped to a particular function. And like the random variable, we suppress the element of the sample space W from it. So W is missing, and we just use this one actually changes to just X. This one changes to just X of t. So when we have X, it's a random variable. When we have X of t, it's a random process. And the emphasis here is that it's time dependent. That time dependent nature actually is the objective of stochastic, and that makes it very powerful and versatile. Just one important thing that I forgot to mention, and that could be placed at the beginning. The word actually stochastic means random. So the word stochastic and random are synonym. And a process actually is a function of time. So a stochastic process is actually mathematical model of a probabilistic or uncertain experiment that evolves in time and generates a sequential numerical values. So it's a time function. It's actually a mathematical model that actually changes over time, evolves over time, and actually it keeps generating random values, numerical values. In case of a random variable, you run it, you get a value. For example, if you toss a coin 10 times, your objective actually is how many successes are there, then you get one value. That is random. The randomness is there. Here, the experiment actually is running, and actually the random process keeps generating numerical values. For example, the stock index of a share market. Every single day you are getting a different random values. So throughout this course, we will be using this term stochastic and random interchangeably. Whenever we say random process, it is a stochastic process. When we say stochastic process, it is also a random process. And the mapping is like here. The element of the sample space actually is mapped to a function. And now we have this one or this one, whether you are mentioning the element of the sample space by small s or w or even omega or any other variables of your choice. So sample space actually mapped to a function space. We have a sample space, elements of the outcomes, elements of the elements consist of the outcome of an experiment, and we will have a space of time function. This space of time function actually is the collection of all possible functions associated with the random process, and at different times a function will have different values. This space of time actually is called the ensemble. We'll define it later, but for now the ensemble actually is the space of the time function, and we can say like the sample is the all possible collection of the outcome, it is the all possible collection of the functions. So the function xt is a member of a family set or collection of functions. This family set or collection actually is the function space or the ensemble. So just mind it, in random variable we have these two terms. X is the random variable and X is a sample value, a real number, which could be a possible outcome of the random experiment, which could be mapped by a particular outcome of the random experiment to X. Now here xt is the random process, and actually xt, the capital and a small xt is one particular member of the ensemble, or we sometimes or in many times we call it a realization of the random process. For example, this one is a realization. So if the outcome is S, this will be the realization of the random process, and it will keep going until a different outcome will change it. When it will change, it will not change depend on the specific nature of the stochastic process. So one of the most important thing is here, a stochastic process or a random process has the following interpretation. Very important one, because that will define the ultimate thing associated with the random process we will consider throughout this course. We will not actually consider these ensembles, functions. Most of the cases, our focus will be very limited. And where it will be, let's see. Now, for experiments, let's say this S1, S2, Sn are the outcomes, and the functions actually are the random process actually assigns this outcome S1 to this time function, first one, and the S2 to second, and so on. Now, here we have the sample functions. Here we have the sample outcomes. If we fix T, that means we want to be static at that time. Then what happens? This dotted line here represents T is equal to T1. At that moment, actually, if you consider that one, each sample functions, each of the sample functions now has a value. For example, this one has this value, This one has this one is a negative but very small value. So if we fix t equal to t1, then we have a number of real numbers, and the outcomes of the experiment, S1 actually is associated with this real number, S2 is associated with this real number, Sn is associated with this real number. So we can consider when we fix time to a particular value t1, the whole random process behaves like a random variable. Why? If you run the experiment, one of the outcome will be generated, and you know that outcome will be matched to a real number. It will not be different. It will be fixed, because once we fix time, the real number associated with the function is fixed. And so this outcome now is mapped to a real number. And that's what we understand about the random variable. So if we fix t is equal to t1, then actually the random process, this one, is a random variable. Is this clear? Anybody is here?
Yes, sir.
Okay, no problem. So if we fix the outcome of the experiment to a particular value W1, for example, actually the figure and our text are not aligned. Let's consider this is W1, this is W2T, this one is X, W and T, and this one actually is W1. So if we fix W1, W equal to W1, then actually we are here. Then actually we have a sample realization of the stochastic process. Then we get a function, and the function actually is keep going. We are generating random values, random real numbers. So when we fix the outcome equal to a particular one, W1, then actually what we have, we actually forget about the other functions. We are fixed to a single functions of the random process, and we call it a realization of the stochastic. Most important thing actually is the third one. If we fix both t is equal to t1 and w equal to w1, then actually this quantity x of t1 and w1, this is simply a real number. What is the difference with the first one? If we just fix t1,
Sir, then x will be a random variable, but
yes,
here it's the real number.
it will be random variable because we have many possible random values. One here, and one here. And what will be mapped to the random process, that will depend on the outcome of the experiment. If you toss a coin and get a head, say head is mapped to this one, this will be one. If you toss a coin, get it tail, if tail is related assigned to 0, it will be 0, right? So we have multiple possibilities there. One of such possibilities will be mapped, and it will depend on the outcome of the experiment. On the other hand, when we fix both, actually we are on the one end fixing the time, and on the other end fixing the function. So time will fix this, and this function will fix this. So we will end up with a single real number, and is a constant. So collectively, what we can say, the x of t and w is a collection of realizations or sample function, and is the, when we have x of t, we have actually collection of random functions, and always actually we have the experiment with outcomes w1, w2, w3, wn, and then actually we call this quantity as a stochastic process, x of t and w. But when you call it t equal to t1, x of t1w, it's a random variable. X of tw1, it's a realization of the random process and is a single function which varies over time. And if we fix both, then we actually end up with a real number, a constant. And when we fix none, we have a collection of functions and we call it a random process. So I think the idea of random process is clear, but throughout the course, we will consider a random process differently. What it is will come. Now let's see one or two examples, very simple one. The first one is consider an experiment that flips a coin. So it toss a coin. Now, if just you toss a coin, then it becomes a random variable. Outcomes are 0 for tail and 1 for head. But if you want to consider a random process here, what you need? You need a function, a collection of function, more specifically. So let's consider we have two functions. One is sine omega t, omega naught t. Another one is sine 2 omega naught t. So one has a frequency double of the other. One has a frequency which is double of the other. And what we do, how we map it, if the outcome is a head, then xt maps w to the sine function with the lower frequency. And if w equal to tail, that means your experiment produces a tail, then actually it will be mapping to the other function with a double frequency, like this one. So this darker line has a lower frequency, cycle length is higher, E is associated with head, and the light line middle is associated with tail. And if you keep tossing, the random process will keep changing the function, and the realization will be a mixture of two time functions. Now, I think you are familiar with the term FSK. Actually, I think it is written in all cap. Right? Anybody can tell it what it is?
Frequency shift key.
Right. So in frequency shift keying, what we do, we actually assign different frequencies to different number while encoding. Here we have two frequencies, one for 1, another one for 0. So the outcome of frequency shift queuing now becomes the ultimate realization of the random process. And you can study that. Now consider this in a different way. Example 2, we have a random variable A, which actually is defined or distributed uniform 0, 1. Just taken from the book. That's why actually it says it can have a value 0, but cannot have a value 1. So we can have any real values in between 0, including 2, 1, excluding. Now we can define a random process xt, which actually multiplies the sine function sine omega t with the random value. What happens here? We have infinite number of time functions. And actually, the outcome of the experiment is changing, automatically is mapping from one time function to another one. If the value is sine function has the value say 0.25, this is the function. If the sine function has the value, sorry, if the random variable has the value 5 and it is mapped to this sine function with the maximum value 0.5, if the sine function, if the random variable a has the value 0.75, this is the time function. And so only 4 are actually shown here. You can have infinite number of sine function. So now comes the ensemble concept. The family of functions, the collection of functions, the set of functions that actually are associated with the random process, the stochastic process, is called the ensemble. So ensemble, like the sample space, the collection of all outcomes, the ensemble is also collection of all functions. It can consist of an infinite number of functions, as we have seen, or it can consider finite number of functions. Usually we assume that it should be at least 2 or more. An ensemble can be considered as having 2 directions. One is toward time, another one is toward realization. Just look at the diagram here. We have the time direction here, and we have the realization direction here, downward. So when we have the direction along the realization, it is pointing the different sample fields and are selected by the outcome of the experiments. And the time actually is selected by some other parameter or some other criteria of the stochastic or random process, maybe by some event. So we have the ensemble considering in the time direction. When we go in the time direction, most of the cases what happens, we are fixed with a particular function. And toward realization, usually time is fixed. One of the function is selected. Given a fixed sample point or outcome, we'll have a fixed function and we will actually proceed in the time direction as I mentioned. And given a fixed time, actually we move along the realization. And the realization actually gives the possible values of a random variable. This is the repetition of the same figure. It tells that along the time we go in this direction and usually we fix to a particular function. Along the realization, actually when we have different time functions and actually we get a value. So here one important thing, and this is a very single line, it is bold, and throughout the course most of the times when we will be considering a random process or a stochastic process, our objective will be to consider the random variables in the stochastic process. That means all the times we will try to, okay, the time is t1 here. As soon as we fix the time there, we will consider that a random variable exists there. And so we will denote that one as a random variable. For now, let's consider when t is t1, x of t1, actually, as time is fixed here, it's a random variable. At time 2, now let us consider somehow we have a stochastic process that actually is considering mapping, counting the number of cars that arrived in the parking lot of I unit. So as soon as a car arrives, the number of cars increases. Say at time t1, 1 car arrives, and we have a random variable there, xt1. Xt2, we have another random variable there, and number of cars arrived so far is represented by this one. So we can consider that a stochastic process is a collection of random variables, maybe infinite in number. So whenever we will consider a stochastic process, we will consider this way, and it will be a collection of random variables. So our views toward the random process will always be a collection of random variables. If this is the case, many of the things that we have learned previously now will be applicable. So all the rules, regulations, the theories that we have learned as part of classical probability, which we now can call classical probability, are applicable here, but in a different perspective for a different set of objectives. We will consider them later. For now, our objective will be to consider that it is a collection of random variables. In case of a stochastic process, our objective changes. We want to actually identify the relation between random variables. We want to identify the boundary conditions. What do you mean by the term boundary conditions? Let us consider a router. The boundary condition represents whether the router buffer is full or not. Or what is the probability that the router buffer is full? And this indicates whether the network is congested or not. We can consider from an ATM's perspective whether the number of customers, clients, persons in front of the for a particular ATM machine is 0. Then it indicates we also actually full or not, or 0 or more. In case of this, full actually is the boundary condition and leads to congestion. In case of this, 0 indicates idle. And if we can find the fraction of time such a machine or such an ATM machine is idle, actually leads to one very interesting quantity for the management, the utilization. If the utilization of an ATM machine is very less, actually it is meaningless to put it there. For example, in IoT, now we have 2 ATM machines from the everywhere. What happens? Previously, there was one, and another condition actually is here. Say the number of persons in front of the ATM machine is large. That means customer satisfaction is very poor. That's why a second ATM machine is installed there. So for a stochastic process, actually, in many cases, all of these actually can be represented by random variables, random quantities, probabilities, but our conditions, our targets in many cases actually will be on the boundary conditions. In some cases, we will be interested in knowing the steady state behavior of this system. What is the long-term outcome of the process. For example, you have a machine. When it will be in operation, you will find that it is out of order, it is working. So, and when it goes out of order, fixing requires time and money. Money is one thing, time is actually the customer satisfaction might change because the service will not be there. And now you need to calculate whether it is better to fix it frequently or you need to replace it. That can be done by the long-term behavior of the machine, studying the long-term behavior of the machine. So one actually takeaway from this is that all the times we will be considering a random process as a collection of random variables. Unless otherwise stated, throughout the course, we will be considering that a random process is a collection of random variables. Now, mathematical tool, probability models associated with random process, which actually is a collection of random variables. Every random variable, as we already learned as part of the classical probability theory, can be characterized by a probability model, which can be a CDF, irrespective of whether it is a discrete or random variable, or sorry, continuous random variable, and a PDF or PMF. So if it is a continuous random variable, we use PDF. If it is a discrete random variable, we use PMF. Now, if we consider T is equal to T naught, then X T naught, as we mentioned, now is a random variable. And we can have the PDF of this random variable denoted as, by mistake, PDF X for the random variable, and having the value X at time instance T1. That means if we go back here, then we have actually fixed time here T1 or T0, and the value we are considering what is the density that the value will be this one, or this one, or in case of a discrete random variable, what is the likelihood that the value will be any of this. So this quantity is the PDF of a single random variable, but mind it, it is at time T naught. At different time, the PDF might be different, or the PDF might remain unchanged. So when it remains unchanged, we call it stationary. It is not time dependent. So we can have the CDF, we can have the PMF like. So let us consider the third example, telegraph signal. Say the binary values are transmitted. Now, how long a particular binary value will be there, 0 or 1, as a continuous signal? It is an exponential random variable. So that is this duration is an IID exponential random variable. So the first one actually is T1. The process starts at time 0, T1 here. This one is T2, this one is T3, and so on. They are IID exponential random variable. Now, this is the random variable. The values. Okay, this is the random variables, and now this stochastic process actually is binary valued, and the time samples, that means if you take any samples, for example, at this point, the sample has a value 1. At this point, sample has a value 0. So the random variable is binary, binomial, sorry, Bernoulli. Random variable is Bernoulli. And so the time samples are Bernoulli random variables. So each of the values at a particular time point associated with the random process, if you look at here, we call it a time sample, actually will be a Bernoulli random variable. It could be 0 or 1. Now, if someone asks what is the probability that this random variable, let us have a simpler notation, x of k, that means at time instance tk. So we are interested in knowing whether it is 0 or, and more specifically, we are interested in knowing this one. So what is the probability that this one is 0? This is one thing. If there are n transitions in the interval 0 to tk, what is the value of xk or x of tk? Actually, it is n mod 2. If we can see, after every odd number of transitions, the value becomes, this is number of 1, this is 2, this is 3, this is 4, this is 5, and this is 6. So after every odd number of transitions, the value becomes 0, 1, and after every even number of transition, it becomes 0. So x to k is, if n is odd, then it results in a value 1. If it is even, then it results in a value equal to 0. So we can easily understand based on the number of transitions, what is the current value if we can keep track of the number of transitions. And the probability that xtk, or you can write it xk equal to 0, is this one. Due to its exponential nature, the probability will be this one for long term. This will be 0. When actually, since this is exponential random variable, and we'll try to derive this one, hopefully, as part of the Poisson process when we will be studying this one. But for now, assume that the probability that xk is 0 is this one, and probability that xk is 1 is this one. So we can actually define the PMF of xk. It is 1 with probability and it is 0 with probability it is. Sorry. I wrote it in the long order. That's why 2 zeros are coming. The probability is half plus half 2 lambda tk when x is equal to 0. It is half minus when x is equal to 1, and it is 0 otherwise. So we have the PMF since it is the Bernoulli random variable. So we have the PMF here. Now, studying the individual random variables at different times here. At different times, we have different random variables. It's okay, we have the probability model, but if we consider 2 time instances for a certain random process, then at time t is equal to t1, at time t is equal to t2, the PDF describes 2 random variables. We have 2 different PMF, PDFs, CDFs, but what it does not define, does not describe the relation between these 2. The relation can be actually calculated by their correlation, covariance, many other things. But to know that one, what we need the, okay, they might be highly correlated if they are very close to each other. So two random variables that are side by side, for example, here and here, might be correlated, might not be correlated. So to understand whether they are correlated, they are not correlated, what we need their joint distributions. Such a joint distribution actually in terms here we call it a second order PDF or second order CDF or second order PMF. For example, it is something like this. For random process X, the values are X1 and X2. A semicolon separates them to represent that this X1 actually is the random variable at time T1 and the X2 is the value of the random variable at time T2. So this is the joint PMF of two random variables taken at two time instances, one at time T1 and another one at time T2 for the random process X. So here we have the random process. Here we have two time instances. Two values. Real values. So the joint probability that we actually usually know this way, two random variables X1 and X2. Now, what are the differences between these two? One is that in case of two random variables, we can have a comma here or it. What we did when we studied the bivariate distributions of two discrete random variables, we have one random variable X1, X2. And we wanted to know their joint distribution, the probability of simultaneously occurring two values, X1 and X2. Same thing is here, but now we do not define the random variables explicitly, X1 and X2. Rather, we say the random variable X1 actually is the stochastic process X at time T1, and the random variable X2 actually is the stochastic process at time T2. So that's why instead of mentioning these random variables separately, we just mentioned that we are considering the joint probabilities, joint PMFs of the random process X. The sample values here, real values, are X1, X2. So now we need to mention, okay, random process is fine. Where are the random variables? We said that the random variables are right here. One at X, T1 is XT1, considering at time T1. Another one is XT2. Okay, I think you understand this one. And similarly, you can have the joint PDF, you can have the joint CDF, you can have the joint PMF for a stochastic process. And needless to say, when you have the probability model of two random variables, you can have the probability model extended for any number of random variables. So any number of samples taken from the stochastic process, n number of samples taken from the stochastic process will generate n random variables, and we come up with a multivariate distribution. Now, once we have the multivariate distributions, the remaining things in these lectures are very some examples. I will skip. You will read it. Main idea has already been given to you, but one thing that actually is important here. Whenever we have a random variable in a random process, we can calculate the mean function. we can calculate the mean function. How? The random variable that we considered at time t is x of t. It is a random variable. If x of t actually is the random process, actually x of t1 is the random variable, but to make it a general one, we have the random variable xt. For any values of t, we will have a random variable. And since it's a random variable, we can have a expected value or expectation, which we can also be indicated this way, that the expected value at time t for the random process x, nothing but the PDF of the random variable x of t at time t multiplied by its value. You can have this one. If you are dealing with a process that is associated with discrete random variables at time t, how that will be the case? If the set of possible values of the random variable x of t are from a discrete set, then it will be a discrete random variable. If it is R from a discontinuous set, then it will be a continuous random variable. Okay, I think I need to spend few words here. This one actually is a random variable. Question is whether it's a discrete or continuous random variable. It will depend on the ensembles, the functions. If the functions are actually giving at a particular time discrete set of values, then it is a discrete random variable. If they are giving a continuous set of values, then it's a continuous random variable. It's a sine function, values are continuous. If you consider it's a squared wave, you will find discrete values. So x of t can be a discrete random variable, can be a continuous random variable. And on the other hand, this t, you can consider this t also from a discrete set or from a continuous set. So we have actually 4 situations here. A random process where actually the random variables are extracted at discrete time points. A random process where the random variables are considered at continuous time points. One, actually the time parameters will actually categorize the random process into 2 different things. Also, whenever we have the time values, set of time values, we will come up, we'll have set of random variables. The random variables can be of discrete random variables or continuous random. Anyway, the mean function can be calculated in this way. And for discrete time, it is actually many books write in this way, consider this one. Now the telegraph process, we consider this one. What happens in that case? Actually, examples are taken from different books. We had actually here 2 lambda, doesn't matter. We are not actually focusing here values, rather concepts. Then the probabilities are this one, minus, and for x is equal to 0, it is plus. And if you calculate the mean value, then it will be 1 times this one, 0 times this one. So we have this. In case of the sine function, A actually was a uniform continuous random variable. This, then actually this will be this one, and we can consider it will be, because the sine function will remain there based on its value at time t. You will have different expected values, but the uniform random variable, which will have a value half as its average. This sign function we also considered, did we? Then it will have the value 0. Now the mean value that we considered here associated with the stochastic process, this one is statistical average. Because we are calculating the expectation of the random process at time t. However, we can also consider its time average. Over time, whenever we consider it over time, then actually we need to consider a particular realization of the stochastic process. Like the frequency shifting, it will change over time. But if we fix that, okay, the time function is a particular ensemble, then actually we will have this time, one of the functions, and then we can actually consider it from a time variable from -t to +2, and we divide it by this one, the integration will divide it, and for t as large as we can, it will give us the time average. So due to a delayed start at 11:05, we will consider 5 more minutes, hopefully. Remaining are not very important, just some definitions, some things. So one more thing here, we will consider what happens if a statistical average is equal to time average. So for a stochastic process, if the statistical average and time average are equal, we call such a stochastic process an ergodic stochastic process. And we will cover it in detail in Markov chain when we consider discrete time Markov chain, because ergodic Markov chains actually exhibits a very important property. Now, I'll just skip showing it because we will actually once again come to the known things. In the last class, I discussed that correlation actually is the relation between two random variables x and y. How do they correlate? Now, we can have a correlation between two random variables associated with the same stochastic process, but considered at two different time points. The correlation of such random variables that are associated with the same stochastic process or random process is called autocorrelation. The formula remains the same. And we can define this one in this way, autocorrelation. For this one, the sign function. You can, it will be very interesting to identify. Actually, I'll upload the slides on Monday, hopefully, why the value is 1/3. It is consider it is a home task. Try to identify why it is 1/3. What did they actually, these are examples. Just see it. We'll find it. Now, another one is if we can calculate the autocorrelation, actually, we can also calculate the autocovariance. Simply, like before, the autocovariance actually is the covariance between two random variables that are taken from a single stochastic process at two time instance. And we can have this formula, this known one. The example is given here. Okay, we'll finish this with this one in one line. A stochastic process that is called stationary if the random variables at different time instance. This one with joint probabilities, this one actually, so far we have written it in this way. But you can consider these two are identical. If this one is equal to this one, what is the difference? There is a time shift. If a time shift to a set of random variables does not change the joint probability, then we say they are stationary. They are strictly, in fact, stationary. On the other hand, if they are independent, then we have this one, IID. Okay, this will be considered, we will start with the next class with this one, white sense stationary, and the strict sense stationary autocorrelation we discussed. We will finish this 1 minute. And this is, now we can classify stochastic processes into 4 categories. The first one, the time is continuous and the values associated with the random variables are continuous. Both are continuous. We call continuous time and continuous space or amplitude stochastic process. Here, time is continuous, but amplitudes are discrete. We say continuous time but discrete space stochastic process. This one, discrete time but continuous state stochastic process. And this one is discrete time and discrete state stochastic process. So in general, we have these 4 types of stochastic processes. We mainly focus on stochastic processes that are discrete state. That means possible values of the random variables are discrete. Electrical and mechanical engineers usually are more focused on stochastic processes that are continuous valued as well. So that's all. We finish this one, except this quantity that actually it requires some time. White sense stationary and strict sense stationary. We need it. That's why we will actually define it in a later class. We'll start the next class with this one. So we are finishing. You are section 1, right?
Yes, sir.
Okay, thank you very much for joining.
Assalamu alaikum, sir.
Alaikum assalam.